I'll make the introduction first. We can wait for a few minutes. Students are always late.
Let me share my screen.
Share, yeah.
Where is that? Maybe it's good.
Is there any video? You want to share sound or?
No video.
Okay. Can we make it full screen so we can text it? It's sharing the other screen. Yeah. This is your screen, not that one.
Okay.
I think what we did before, yeah, we have an expert who is out on travel this week on IROS. So let's share, stop share.
Maybe share the screen.
Yeah, share the screen set of the PowerPoint. Yeah. Let's try. It's the other. Yeah, this is your screen right here. Screen 2. Okay, there you go. Okay. Good. Yeah. Okay. Oh, the fucking back. Yeah, thank you very much. Appreciate it. Yeah, there are a lot of tricks every time. So yeah. So I'll give background. There you go. Thank you. It's the best seat. Reserved for you guys. For students, you got coffee, you got cake, so grab something. All right, good afternoon, everyone. Welcome to today's ICON seminar. My name is Zidong Wang. I'm currently assistant professor in civil engineering and also assistant director of ICON. And I'm in charge of this ICON seminar series with my colleagues, Professor Guin from EC, who is out on travel at IROS in Abu Dhabi. Pretty jealous. And Professor Yelia Lee. And today we have another industry speaker, Dr. Ehsan Moradi-Pari, and he is currently a division director and chief scientist at Honda Research Institute. He's based in Ann Arbor, Michigan. He actually drove here for 5 hours last night and will drive back tonight. So we really appreciate that he came all the way here. Ehsan has been working on this whole domain of connected autonomous vehicles and human autonomy teaming for quite some years. Now he's leading two different divisions at Honda Research Institute, and has been looking not just for autonomous vehicles, as many of you might imagine Honda is doing, but they also do a lot on robotics, on human autonomy teaming. So I think a lot of you are working on robotics, not necessarily on autonomous vehicle, and you might benefit a lot from his talk today. He's talking about human autonomy teamwork. So it's a very hot topic, as I personally also work on human autonomy teaming, so I look forward to that as well. But before that, I want to introduce a little bit further. He has been very active in representing Honda, this whole company, in different association. If you were here 2 weeks ago, we had another guest from Qualcomm, James Meisner, was talking about 5GAA, that big consortium. Ehsan here is a representative for Honda on that big consortium. He was representative from Honda on different research program as well. There is another one called CAN, which we just realized that both of us we worked together back in 2017. And he's also on the advisory board of this Universal UTC Center of USDOT, CCAP Center. Some of you might be working on CCAP projects. And today we're very happy to have him here. He had a very successful launch session, talking to some of you, the students, very fruitful discussion, and we're gonna hear him talking about human autonomy teamwork this afternoon. With that, let's thank the speaker.
Thank you very much. It's my pleasure to be here, and I enjoyed the driving. It's a fall season, beautiful. That's why it's my absolute pleasure to be here. Today I'll be talking about human AI teamwork. The title is, I try to make it fancy, but Mastering Human AI Teamwork, Dynamic Role Assignment, Knowledge Representation for Adaptive Multi-Agent Cooperation. And it was interesting from 11 a.m. that we start talking. There were many synergies between what you guys do and this topic that I'm presenting. Some of you are actually focusing on some aspects of what I will be presenting. That's why I'm also looking forward to engaging in dialogue with you because I can also learn from you as well. That's very interesting for myself. Okay, we go to the next. Okay, yeah, that's fine. So why multi-agent? First of all, why what can we not achieve with a single agent that we are looking for multiple agents? I think it's very organically baked in how human society evolved throughout. Because if you look at like the history, there were some colonies or countries that they started to expand on technologies and things like that by working together, by having different technology to go over different places, and by connecting people with each other. We were able to reach these societies that we have today. If everyone stayed at where they were, maybe we didn't have today's world. And it's come basically from that. From robotic, if you look at it, if you go back in like the few years ago, we had a time that the robots were put in a cage in like factories, a single robot in a cage. But that evolved. They came out of the cage. They started to look at multiple heterogeneous, homogeneous robot, then heterogeneous, and now they're everywhere. So they're not in the cage anymore. They live with us. They're around us, and we leverage their existence because they are there to help us. That's where it comes from and why we need a multi-agent system, because we cannot achieve it with a single agent. Those tasks, we need a multiple robot to cooperate. If you look at it from, this is from my own, it's nowadays something very, let's say, scientifically proven that you say, okay, this is my own roadmap of how I look at it. I started with autonomous cars. There were no human. The topic that we worked on and I worked on was to realize a more efficient driving experience. I work for Honda. I was working on connected automated cars, driving experience. And we wanted to make a movement in synchrony with others. I am using since morning this example of someone on a merge joining the main traffic or on highway or at the intersection. But the key thing for my research has always been to be mindful to the impact of the decision I make on others. For connected automated car, one interesting example I have for you is that there is a program in California. It's called Autonomous Vehicle Testing, AVT, that if you go to California DMV website, you can find a link to the latest reports of autonomous testing and disengagements and crashes and things like that. If you look at the crashes, the majority of the crashes that happen, or a good portion of them, if I don't want to say majority, a good portion of them are caused, are scenarios where you cannot blame the autonomous car per se, because it's a rear end collision that a human driven car had accident with the autonomous car. Where that comes from? Is it because humans are not cautioned enough, or human driving is not safe enough? I don't think so, because we have human driving since when? Since the invention of the cars. But one hypothesis is that even though autonomous car making a very safe decision for its own, but it does not necessarily a safe decision for others. Maybe it's a selfish decision that the autonomous car made for itself. It's a very good decision making for itself, but it does not map to the human-driven mentality, because most of these testing efforts for autonomous or simulation you use, the driver, when they want to mimic a human driving, they usually go with the average driver behavior in the model. They don't have as much aggressive driving that you see on the road. So you cannot get this sense in simulation when you do your designing your algorithm, but later you go on the road and you see that kind of behavior. So one of the key aspects is to be mindful to others, meaning that you look at how you make your decision and what would be the impact on the other surrounding. This was my research when we were working on swarm of the cars when they move after each other. They travel together on the road and highway, and the goal was to enhance the throughput of the highway or the road that we're working, how we can reduce traffic, how we can make a better fuel economy decision for the car, don't have more sudden jerks or like hard brakes or things like that. Try to make heavy the smooth to have a more fuel economy type of thing. This was my research for autonomous cars. And also I worked on V2X related topics on how to get V2X, come up with protocols. At some point, we sit down together with other colleagues and we wrote a standard for cooperative adaptive cruise control. These were the research I did here. But so far, there were no human action. Of course, there are some human action in or human personalization in autonomous car research as well, but I did not focus on those. Then we said, okay, so far it's autonomous car making decision. How can we coexist with human? That's where we shifted a bit my research more toward the social setup. We come out of the highway and we went more to our social setup, where you have pedestrians, you have these smaller robots moving around you and all those type of environment. And we still looked at the same problem, how we can have a multi-agent that we can maneuver or go or have our task or achieve our targets in coexistent with human. In these cases, we just try to avoid collision with human, meaning that the robot does not get close to a safe zone of the human or the human zone, or how we can facilitate in a way that we do not block humans' way, or we do not block the traffic and make the flow even worse. The picture I had, the first picture when I brought my presentation up, that's from a intersection, that's the most crowded intersection on Earth, and Tokyo, where when it starts, like people are walking, you have to be there to see what it is at like 7 p.m. or 6 p.m. or 8 a.m. to see the crowd and things like that, the flow of human. And see, if you want to introduce a technology there, it has to coexist with those humans. The next step toward this human machine cooperation for me is that the system that gets feedback from human. If I want to upgrade my system, so far I have been coexisting with human. It means that I was avoiding having collision or getting into the human comfort zone. But now I want to have a system that get feedback from human. It means that it listens to human, it gets some policy from human, it adapts its behavior toward that. If I can upgrade my system to this system, then later on, I can have a full collaboration with human. If I have a technology that I can modify my decision-making based on the feedback human tell me, then later on, I can add more stuff and upgrade it in a way that 3 robot and a human can lift this from here, take it outside in harmony and collaboration with human. So end goal for me is this one, collaboration with human. And I want to have a system that collaborates with human. And now I try to attack it from different perspective. Because if I want to have a team that human is also part of it, I need to deal with multiple things that I will be explaining in this presentation, from forming a team itself to working with human, to representing knowledge to human, and also to adapt to a new human. Because we are looking at system that we do not necessarily have a system that the agents in that system know each other from the past. They do not necessarily need to know each other. So that's where we are coming to this topic of cooperative humanistic AI. What does it mean? It's an AI system that from the definition that works alongside with human. Also, it emphasizes on potential agency of human. What does it mean? It means that these robots or these systems are not there to remove the completely take the job from human and do it and then deliver the result. No, we want to respect, because most of the time, if you go to the social psychology and things like that, we like to have agency. We like to have agency and control over some of the things. I don't like to be served all the time. That's not what we want. Of course, there are times that we want to be served, but not all the times. And we like to have that type of agency. So we want to design a system that works in a way that delivers the sense of agency also to human, and we do not remove that. What do we need for this? Cooperation becomes a very important thing. We need to enable interaction, negotiation, communication, and teamwork setting. Ad hoc adaptability is another thing. Ability to engage with human with a minimal prior knowledge. It means that I do not need to know the whole things about this human. A robot doesn't need to know the human that participate and works with it from the past. It's not a pet robot. It's not something that you interacted with it all the time, that it knows you somehow, or the mental model of the robot and human, because as they work, if it is AI, they get close to each other. The robot tries to adapt itself to the mental model of the human, which is, in some literature, it is called personalization. But imagine we don't have that. We don't necessarily need to have that. If we have it, it's good, but it's not needed. That's what I try to say. And human AI alignment is another thing, which means that we ensure alignment with human values, behavior, and also human action. You're from academia. I need to have some hypothesis for you first. So we go to the hypothesis portion. We are making these are the hypotheses that we do for this. First of all, it is feasible for heterogeneous robot to form a team for a certain task with a partial knowledge about teammates. Hypothesis number one. Hypothesis number two, there exists an optimal coalition of robot that that these may be disengaged from their primary task and take on a secondary task that it comes. Remember, I was talking about ad hoc adaptability and less prior knowledge. It means that this system is not designed just to do this, lift this and take it out. It was designed for multiple things. And this is ad hoc task that they come help me and then they vanish and go their own job. That's another hypothesis. Another one, it is possible to collaborate, coordinate within a team in an ad hoc manner to adapt to a new secondary task. There exists an optimal representation of the information about agents and environment that facilitates team formation, and also it helps achieving a higher performance on the desired task. And also considering a social metrics in negotiation design with multiple robots would improve the crowd. If we go with the social norms of that society, we might be able to help with some of the aspects of that engagement. From the design perspective, we need to have some notions that these are criteria for our design. Of course, we need a decentralized framework. Having centralized all the time does not necessarily solve. It's not scalable per se. So decentralized is a key. Real-time decision-making is also another thing. We want to design a system that works in real time. We don't want a system that we hit the switch and start the work, then it works. It does sophisticated computing and things like that, but it takes time. By that time, maybe we don't have the need for that teamwork to happen. So real time is very important. Partial observability, another thing. Not all the states are known for agents. A heterogeneous robot is another design criteria. Remember, this system, of course, it can be applied to all homogeneous robots, something like Amazon Robotics or a swarm of similar robots. It can apply to that, but we don't necessarily want that because having homogeneous means that we cannot expand on capabilities. If all of the robots you have are ground robots, you can add a drone to it, then your search and rescue might not be as efficient. So you need to keep the door open for heterogeneous capabilities if you want heterogeneous application at the end. Multiple objective. These robots are not designed just to collaborate with each other. They have their own primary job. But when it needed, they can form a team and achieve a secondary one. It needs to coexist with human. Of course, social factor, the way they behave, maybe some of the features from theory of minds would be necessary on how to read and imagine someone else's to close the mental gap. And also ad hoc is another thing. Coordination protocol, these do not exist a priori. They are on the fly. So that's also another ad hoc factor to it. And also imagine you're designing a soccer team of robots that there is also human. The scenario by itself, it depends on the game and how it goes. It's not ad hoc. You cannot find two soccer games that they look the same. No, they're different. So you need to have an ad hoc capability in your design. First, I go toward I try to just scratch the surface for you and give you some idea of what we are doing. And of course, if you need further detail, which I'm sure you're PhD students, you go deeper. There are papers, and also I'm available in case you want to talk. So the first thing is that we're talking about teamwork. The first thing is to form a team, to have a team. Yes. And then decide the role assignment. Who does what in that team? Who is in charge of what? So role assignment, the way we look at it, we are dividing it to two steps. The first step is to form a coalition, basically who is part of the team. The second thing is the role assignment, is that who does what. And we have to make sure that these role assignment, it needs to be dynamic. It cannot be a role assignment that stays until the task is done. Many things happen. This is a teamwork. All robots, they have to have the option to withdraw from the mission, or human. They have to, for example, I join a group, I attend that teamwork for 10 minutes, then I have something else I want to go. When I leave, someone has to do what I was doing, correct? So we need to have a dynamic role assignment. Again, maybe some of the role needs to change based on the status of the work and things like that. So this role assignment has to be dynamic. It cannot be a fixed role assignment. One example of how we solve this is like this market-based actions, that there is a robot closer to the task that it is. It announces the task, it receives feedback of help from others, and then based on that, it does a task allocation. This morning, I saw a very good presentation of task allocation, I think from Giron's team, that they were working on this task allocation for heterogeneous capabilities. And then the team formation helps. There is a market-based strategy for this. We design a utility function for a specific task based on availability of them, affordance, and all these notions inside it. And then we assign the task, and we have been showing that we can improve the state of the art on this case. Also, if you look at it, I was talking about the decentralization, but now it might come to you, okay, that robot guy there, the green one is doing all the work. It's not decentralized. The others will raise their hand, and this guy gets to decide and distribute and things like that. If we have this, then with a simple consensus algorithm, we can even distribute that. So that's not a big challenge here. And we are showing this. Also, we are expanding this. This is just a market-based strategy toward it. There are other solutions for it that we are also looking at it. Then I go to the cooperation scheme. Now, what do I mean by cooperation? The problem set up, we need to pick an application to show the value of that gradual change from no human coexisting with human to feedback from human to collaborate with human. So the problem set up for it is to design a multi-robot distributed socially conscious navigation algorithm in human crowd that we can influence the human crowd, and also we can help the traffic flow of that and avoid any things like that. If you look at it there, that's a multi-agent distributed multi-agent distributed system. We have some social criteria for it, which we call it social consciousness. First, keep comfortable distance from human. Don't get into the comfort zone. Do not cut in front of people. People don't like to have that. That wouldn't be very impressive movement from a robot in front of a human, and it wouldn't encourage further cooperation between human and robot. I say, oh, this is a selfish robot. Yeah, why would I bother? And then follow social norms. In some societies, there are some, I don't know if you have been to Tokyo, for example, if you are standing on escalator, everyone stays on the other side of the escalator. It's not like US, we stay everywhere in that escalator. But there, it's more crowded. So the way for someone to walk on escalator has to be open. And depending on the city, they either stay on the right side or the left side. You need to know even that one. So it's important to follow the social norms in that society when it comes to navigation. And We have some notations. We have set of robot, set of human, position, speed, acceleration, state, and control actions. And we have some assumption that the robot and pedestrian real-time position, these could be obtained. Basically, you have a positioning system. And also the robot and the coordinator can exchange information. We have some way to exchange. If, for example, if three robots want to navigate together, they need to know each other's direction, position to make a better prediction and decisions. This was the problem, Sada. The way we solve it is that this work was published in ICRA and IRAS both this year, and it will be presented as we speak in IRAS in Abu Dhabi. One of my team members is there and presenting in UAE. So we solved this problem by making it, dividing it to two problems. First of all, multi-robot coordination. We map it to a potential game. What does it mean? This is for robots coordination with each other. It means that the incentive for a player of this game, based on the potential game theory, if you go read it, the incentive for one player to change their strategy aligns with the improvement that it can cause for others in that, meaning that the more mindful it gets, it can also make decision along the line that this decision is also good for others. And then this is for the robot coordination, a potential game, and then a two-player game, that's another theory. It's between group one, which is human, which is robots, group two is human. And then we had a data-driven MPC with social LSTM was also used for the trajectory of human creation and prediction. And we showed that we can improve the traffic flow with this design, having a distributed solution for this. And we can even show that these robots, the blue ones are the robot, the others are human in simulation. And even we have a capability to let you, for example, with a joystick, control one of these human and change your mind to see if you think these are pre-coordinated or not. You can walk and then walk backward and things like that and see how the robot behavior changes in that sense. The next step is that we try to investigate hard safety constraint, more social metrics, reduce computation and time, and go for more like sampling based, because these has to work in real time very well. And also multi-agent RL is another avenue that we can stretch this work. One thing that I am very passionate to talk about this one, is because if you remember, I was saying coexist with human, then go to feedback from human, then collaborate with human. So now I want to enable human in that. So far, coexist, because it doesn't collide with human, or it doesn't get into the comfort zone of the human, and it follows social norm, but it does not necessarily move in that direction that we can bring human to this cooperation. How to make it happen? Empowerment is an interesting concept. If you go read the social psychology definition of the empowerment and the affordance and autonomy that it can provide for human, the goal here, the way we bring empowerment in this framework, is that we incorporate an interesting motivation model in planning a scheme of these robots. And when we try to make the group of robots socially compliant, basically the robot, when they want to decide their movement, they think how it will impact the empowerment of the humans around them. And if I can formulate this into decision making, then I can adapt based on different human sense of agency as well, because I can reduce and increase, play with that empowerment. And I can bring, I can adapt the robot behavior based on the sense of agency that the human that I am interacting with is wanting or desiring to have. The empowerment, this concept is rooted in information theory, basically measuring the extent at which an agent can influence their environment. We define this as a mutual information of an agent's action and resulting in future state. Basically, the higher, if I can open this door for human and beyond this door, there are 10 other doors for human, compared to if I open this door and beyond this, there are 3 doors, the 10 door gives more empowerment to human. It means that it enables more functionality and it offers more option to the human. That's why it increases the empowerment. Also, the key idea is that we empower the agent to achieve its objective while it is retaining the flexibility or adapting or even expanding that meaningful decision toward the human that it cooperates with. The key insight from this work is that the higher empowerment implies greater control over future states, and also optimizing robot policy to maximize this human empowerment. If we can formulate it, then we can optimize it. The first problem is to formulate it, which we have been able, and we submitted this work. It's currently under review, and we're trying to define empowerment as a new KPI or a new social metric for cooperation and for navigation. And that's another work. And after this, the sense of agency would be much easier to achieve. I changed that topic to knowledge representation. I think everyone is familiar with this one. This episode of Friend, where they try to take one couch to the second floor and the lack of coordination between them, and Ross is calling pivot, whatever. If you haven't seen, go watch it again. But we are trying to say it's a multi-agent task, because there are 3 humans that they want to lift something, and it gets to a challenging that they need to be very well coordinated with each other, and they need to have that type of coordination with them. So what do I mean? The task-aware human interpretable knowledge sharing. If we have a group of human and robot that they try to achieve a shared task, they should be able to represent their knowledge and also their action in a way that the human also understand it. If I have 3 robots, 1 human, we want to lift this, those 3, they can coordinate with each other, but I don't understand it because it's a machine to machine kind of information exchange, that there is no reason, there is no a human sense of context and things that we use when we want to explain to each other. They might say 2 up, 3 down. I don't understand it. I need to say, okay, lift it from ground to top, and in a way that I also understand as a human, that I can follow what they do. So that's the core essence. How to find the best representation that enables human interpretability, and also it still achieve the task accuracy. Because the machine-to-machine communication, it's optimized for the task. They communicate in a sense that they can achieve that task the most accurate way they can. But that's not human interpretable. If they make change in their negotiation, we might lose the task accuracy. How we can compensate for that? To have the accurate task as well as the human interpretability. We thought about it. 2 solutions is possible, at least what came to our mind. First of all, design a new knowledge representation scheme for a group of human and robot. That's that one. It means that from the get-go, we have protocols and knowledge representation scheme that human understand it, robot understand it, and it flies. That's one. Second of all, is that the existing system, we have machine-to-machine cooperation. Can we influence that one and make it human interpretable or not? That's the second approach. Assuming it's not a big assumption. We have it. Machine to machine cooperation, information exchange, and knowledge representation is there. We want to see how we can influence it and make it human interpretable. That's the main challenge. I would show you how we try to push the science boundary in both of them approaches to find the best solution for this. For approach A, the way we are attacking it, it's a neurosymbolic framework for knowledge representation. I think all of you are familiar with neural network and knowledge graphs. Each one of them has its pros and positive and negative. Of course, for neural nets, high dimensional output is very important. Output to single, multi classes is another one. But the problem there is not interpretable, it's not explainable, and it has those challenges. Knowledge graph, on the other side, it is interpretable. It can be extended anytime. Human interpretability is there. But if we combine these two, I think we have the good side of that neural network and also the interpretability that we expect for knowledge graph and also expansion of it for multi-agent teamwork. So we try to develop a neurosymbolic reasoning framework. For static, we have something called compound concept understanding. That's what we are attacking. Also dynamic inference. We have action understanding using global observer or agent point of view or partial observability of the agent. Also, we have predictable policy learning, meaning that when I, as a robot, want to have human interpretability, I should make some decision that it makes sense to humans as well. So I try to move along that making sense and common reasoning for human as well. And we have a distributed scheme for knowledge sharing. Compound concept, this is basically not only detecting the object, but also the relation of these objects. And this one, it's just more than just a group of common individual objects. They relate to each other. For example, if you look at a scene where there is a, I don't know, multiple microwave or also dishwasher or thing, this could be a kitchen. Or it could be a shopping, electronic shopping area that they sell electronic. That's why they have all of these together. Or it could be a kitchen view. The way we understand this is through this compound concept. And I think we did this research and we published it. It's probably Accra last year or this year. And then the second stage of it was action anticipation. We use diffusion models, and we also use we use these. The main challenge here is that the diffusion models are how to map it to the discrete kind of space, action space. This method, we use a knowledge graph and scene graph for initializing the diffusion model, and we try to enhance that. We tested it on multiple frameworks like breakfast, 50 salad, and the ones that you probably use it for your also hypothesis testing and experimental setup. These are the available data sets that we use, and we have submitted this work to IJR, which is a very well-known robotic venue for this type of work. So we started with action anticipation, and now we are going to our neurosymbolic. We set it up for a single agent already. We are expanding it in a multi-agent avenue as well. We go to the second one, the second approach, which was that we have a machine-to-machine communication, how we can influence that to achieve a human interpretability. Now, LLMs are interesting. If you look at the problem by itself, these kind of icons I have, they're showing different mapping or different representation. For example, that one, hectagon, those are interpretable by machine. The circles are interpretable by human. First of all, when this one comes here, it looks like this, that human does not understand it. When you pass it through, you can use LLM here as a weight, because if LLM understand it, then human understand it. So that's why it's used in that. Then we try to have a feedback from here, the human interpretable version of it. We try to have some feedback for the machine-to-machine communication, enable to optimize that representation in a way that they all understand the same thing, and we can map it to human interpretability. That's the problem statement. We are attacking it from two different perspectives. The first one is the perspective of traditional communication, everyone using auto encoders and encoding, decoding, that type of auto encoder. The focus point is to finding the representation that is most meaningful and relevant to find for the task, basically. And the data is coming, there are some assumption data is coming from multiple, so they may have correlation or not. And also they're considering this correlation. We want to find a useful representation for that. Agent can collect the data and process that, and also process distinct data, but correlated, but they do that independently. Imagine you have several agents that they're doing a search and rescue in one environment, and everyone represent what they want. And this morning, when after talking to some of you, I was happy to know, for example, she has a multi-view reasoning, which is something that is also useful aspect of this, because different agents are looking at one event from different perspective, but they try to reach the agreement that they're talking about the same topic, and they try to reason about those. So the key question is that how agent can efficiently find and remove redundant part of the data. And remember, these are all for now, it's a machine-to-machine communication, first of all. We have a bandwidth limitation. Some of you are communication engineers, you know that we cannot send whatever it is. It doesn't work that way. There is a limitation on amount of information we can exchange. How to find the most useful information for that? It's a question here. We designed a neural distributed, and you know PCA. This is a neural distributed PCA, NDPCA we call it. It measures the importance of the information using singular values, and also it trains one encoder to compress the distributed data. The DPCA that we use, we published this work at NeurIPS last year, and we showed that this approach, the neural this DPCA, is very useful in finding the most representative information while having the communication limitation on that. And we tested it on different environment, like NeurIPS. When you publish, you need to show your science works on different application domain. We had on two different applications. For example, making something task-aware does not necessarily mean making it very crystal clear. For example, this one, if you look at it, that's an airplane. This one is the best representation for task. You don't see an airplane in this. You can distinguish, but for task, it wants this one. It doesn't necessarily want that one. So how to come up with this in a distributed fashion was the challenge. The next step for this is that, of course, there is a task loss, there is a reconstruction loss. We try to have a trade-off between these two and play with it to achieve the highest accuracy on the task. We also tested it on three different data sets, the classification task, locate and lift task, and object detection task. And we showed the value of this method in all three aspects, and the paper is available. I would encourage you to go read it deeper. This was the autoencoder way. Now I go to MARL-COM, which is the multi-agent reinforcement learning communication. It is another strategy of looking at the same problem. Of course, it offers optimal task performance. It's a centralized, demanding training process. Also, it is not human interpretable, this MARLCOM. We have AI agents that they are working based on, this is the, first of all, I try to show you the background domains that they influence this research. MARLCOM, AI agent with LLMs, and also reinforcement learning with human or AI feedback. The goal here is to enhance the robustness of emergent communication via language priors, also learn human interpretable communication protocols for diverse tasks, not only for a specific task, and also enable ad hoc teamwork using MARL and LLM and human interpretability without pre-coordination. They're not pre-trained for this. The method we use, we collect team behavior. Basically, we collect data from LLM and interaction with LLM for the specific domain of work we have. We train MARL to jointly optimize both task performance and communication alignment. Then we map the aligned communication into human interpretable space. This one also, this will be published soon at NeurIPS this year. The other one was last year, NeurIPS. This is 2024. And also, interestingly, we have a, I wish the team was here and they had time that we can showcase it to you. Basically, it's a game environment that multiple AI agents, they work, it's in a predator-prey kind of environment, this one. This type of environment that they try to reach that prey area. But when you add a human, those are working together in the environment and they exchange, but human does not understand the way they communicate. But when we add this framework, adopt this framework, their communication become human interpretable. Human can also collaborate with them and also leverage for their interaction and also interact with them, share information with them. So we could show you the before and after of having a human interpretability while we maintain the task accuracy. The task performance wise, we compare it with other state of the art for achieving that task only, not having human, and we are on par on that achievement. The communication alignment, we have human interpretability there. We have generalizability also, learn to communicate unseen state. Also, the ad hoc teamwork, we show that it facilitates collaboration between MARL. This was accepted recently. And the next step, we try to first of all, these are a very fundamental space of like predator prey. We can only, for now, the technology is at that level of cooperation, the predator prey game or Atari game type. But if you want to transition that to a real world environment, it needs much more work. And of course, a real world imposes a lot of constraint and physical constraint that for now we have been putting that as a side to make the core technology work. But then if you want to adapt to those restrictions, it needs further innovation. But this is also an interesting topic that I like to share with you. Another avenue of this teamwork that we mentioned was the adaptability, meaning that we need to, if it is a teamwork, we need to adapt to new environment, we need to adapt to a new teammate, and we need to learn new skills. Sometimes you need to learn on the fly, and the team work would demand that. You need to be able to learn new skills. For example, you have a delivery robot in the area, you decide to form a team for a search and rescue or a coverage, you want to go around, you need to, that delivery robot needs to learn new skills. So how to make that happen? That's the adaptability that I was mentioning. Ad hoc adaptability is an important one. We approach it from two directions. The transfer learning, basically transfer knowledge from a different domain to a new domain. For example, a kid knows how to ski on the ice, but now goes on the snow. That's one. Also, meta learning is another one, which we want to optimize an initial representation so that the parameter can be fine-tuned on the fly and also effectively with very few samples on the new task, such as this environment that it's a navigation environment adapting to the new environment, for example, within the aisles of a shopping mall or things like that. For representation, for this approach of rep transfer learning, first of all, one of the approaches we are looking at it is policy advising. Basically, like a teacher-student, there is a teacher that observes student behavior and learning process, and that teacher or student provides some feedback to a student, and the student receive that additional information from the teacher. Basically, there is a teacher outside or inside that environment that knows more than you, and it guides you on how to achieve things. The benefit this framework offers, it's a easier training, reduce the high sample that we have. It's a method agnostic. You can adopt any method for this teacher-student framework. It is explainable. We can explain with feedback as like advice in that, and also flexible. It allows for generalization because you do not have a single agent that can do everything. Sometimes that's needed. The benefits you get, first of all, the explanation or the teacher advice. It's not just do this, it's action and reason. So it is explainable. It means that later the student can adopt his knowledge graph or policy using that explanation to the right direction. It is flexible, meaning that sometimes I know your advisors are very good at that. It means that the teacher also adapts to user preference. Like I expect everyone to be in lab, we work together in the morning, but I know there is one of you that works at night very hard. So it's okay for me that you stay at night and work in that kind of sense, that it is flexible to the preference of the student, and the teacher over time learns that how to accommodate for preference of the individual. There is a self-reflection in a sense that the student would be exposed to to explore different unseen scenarios and learn from them. And over time, gradually, we do not need the teacher because the student gets learn to the extent that it could become a teacher by itself. Okay, that was the knowledge base, but in teamwork setup, we are looking at it from two different perspectives. First of all, there are a student with policy, the teacher teaches them different policy. That's one. But it doesn't have to stay in that organically like real world. It's not always one teacher in the world that teaches others to do things. I am better in some aspect, I teach you on those aspects. You are better than me in other aspects, you teach me on that. So the teacher role is not just a role that stays with someone forever. The teacher can change depending on the task, the environment, and things like that. So student in one task could be teacher in another task. You know that. So it's not a role that someone assume and forever play that role. It's not like that. If we wanted it to be scalable, we need to learn from each other organically like real life. So we try to mimic the same thing here as well. And we are looking at both of these problems. This page, I try to bring the papers that, these are all the past year papers that the team has published. The only reason I am bringing this here is that I want to encourage you to take on this. This is a uh, very fresh area that I think you can push the boundaries there. And the area is there for you to come and extend it and add more value to it. The reason why I put these here to tell you that start working on these related topics, you will find a lot of unsolved challenges that needs your creativity to be solved. And that uh, would even help you in your academic work as well as your future job. I think it's a very good area. It's very hot topics these days, especially with advances in AI, with having large language models that could be helpful for many of these. Remember, for many of these human interpretability things, we need to spend a lot of time recruit people to tell them rank if it is interpretable to them or not, and then decide. But now you can connect one LLM, it tells you if it is interpretable or not. So things are getting moving in a direction that it further enables the speed of innovation in this domain. I want to encourage you, as I already learned that many of you are already doing some research along these lines of what I am presenting, but I would like to encourage you to further have a more serious look at these areas and see if it excites your interest. Conclusion, I presented shortly some of our work in 4 different avenues, from team formation to human-machine cooperation to knowledge representation and ad hoc adaptability and adaptability to new domain, teammate environment. Sorry, there are a lot of results that I can present, but due to the interest of the time, I wanted to just scratch the surface and introduce the domain to gauge your interest to go deeper in this area. And of course, I'm available and my team also if you have interest in this topic. And we expect you, because you are smart, we expect you to drive the core science of this from academia side, because you're fresh, you are at the very good school, very good advisors. We expect you to solve these challenges for industry as well, and help the society in general. Future direction, of course, there are some avenues that we are expanding this research, including the alignment. So far, we've been looking on communication alignment, but action alignment is also a factor. We need to make sure about that. It's not only linguistic level that we map our communication to linguistic level, and the problem is, no, we need to have action alignment as well and increase that if we want to have a high performance teamwork. So we are expanding on alignment. Also, scalability and generalization is one thing, and compassionate teaming is another thing. That's also another area that we are working on. Yeah, that's about it. Sorry, I think I took much time, but thank you very much for your attention.
Actually, the paper list that you showed, the EMLB paper, I think it was already accepted.
Yes.
Search out, like,
Yes.
we got accept, so we got not a new publication. But let's open the floor to the questions from the audience. Does anyone have any specific question regarding the one that you showed?
Really great talk. When you're talking about the socially conscious, like coexisting robots, you said they should be like aware of social norms, but then also you have sort of a constraint of maintaining a minimum distance.
Yes.
So sort of in terms of implementing the FBC, what were like, which one of those were soft constraints, which one of them were like hard constraints? Because based on that, you could not have feasible solutions.
Yeah, so safety is always a hard constraint. that one put it aside, but some of the social aspect, depending on the application, could turn to soft versus a hard constraint. For this one, we have different metrics for this, especially that use case of navigation. If you go deep in the metrics of crowd navigation, you will find multiple metrics. One of which, for example, you don't need to collide with someone, don't get close to someone. But some aspects, such as don't overtake from right or left, those could be mapped as a soft constraint in case it needed. And remember, the whole goal of compliance with socially conscious behavior is that you are trying to bring something that human expect and accept as their like cooperation technology. That's something that they can interact with. So you need to be appealing in a sense that this robot needs to be more than just a robot that does work in order for you to accept it, its functionality, or use it more than what daily, like 1 hour, turn it on or off, or interact with it. To have that, you need to perform in a more socially compliant manner, in a way that it encourages other also and you to work with that. That aspect is very important to make it appealing for adoption. That socially compliance is very important. That's why. But you can play with it as your use case is, turns hard to soft or soft to hard, but it depends on the specific use case that you have.
In the teacher-student slide that you showed, I was curious about what would you define or describe a teacher as? Like, is it a pre-programmed report that knows the terrain, or is it like a loss function that, depending on the feedback, it gives a reward or
It's depending on a feedback, it gives a reward, but it's not a pre-trained teacher. So in a sense that it could be in the environment or outside the environment. It could be an observer only, or it could be a collaborator. Basically, two robots, they are doing something. One of them is educating the other one to be, for example, you have a back to the example he had on socially compliance. You had a delivery robot and you have a socially compliant robot. How this socially compliant robot would inform the delivery robot in order to have maneuvers when they are together moving in order to be more socially compliant. So it could be a knowledge graph policy, part of the policy that it doesn't have, it gives it to that, or it could be just a simple feedback based on their capability, because it's not pre-programmed, because they don't necessarily, the teacher does not know necessarily the capability of the student when they start the collaboration.
Great presentation, thank you. So the task allocation and collaboration are mentioning you were accounting for the semantics and distributing all the tasks to each agent. How are you taking into account of how each of the agent might be optimized to do it differently? So, for example, in the like soccer problem, I'm assuming all the robots are in the same position.
Yeah.
But in the collaboration slide, you showed a drill and then another robot.
Yeah.
Ground rover. How are you accounting for what each of the agents is better at a certain task?
So we for that, thank you very much. It's a very good question. We have created a utility function that we try to maximize, and also in that we have an affordance. Basically, when a robot, when we call for a help from others and they respond back, we expect them to raise their capabilities as part of their report back. And then the decision making based on different capabilities that is required is formed. For example, you can have 3 ground robot that they do search, but you only need 2 of them, but you better have a drone than have a top view. That's why it makes a drone more appealing for you, and it increases that, or it optimizes that cost function that we have for optimization we run by having a diverse capability that it offers. So affordance of each agent and their availability is also factored in that, and the task that is needed to be created. So basically, first the task is divided to what we need to achieve that task. Then we look at what availability we have and who can offer what, and then we make the best decision for that team based on that. So affordance is what we bring into each optimization.
So my questions are related to the dynamic role assignment type questions. When you form a team, each member needs to have 1 or 2 or 3 tasks that they will complete. But if it's a very simple task, mission is very simple. Each robot can only achieve 1 or 2 tasks and need 3 or something like that. But if it's very complicated, you need like 10 robots, each one might need to have 10 different tasks or something like that. So at the end of the day, I think you need to be able to have a systemic way to optimize the portfolio of robots.
Yes.
Is that something you consider?
Yes, we consider that, and also redundancy is a factor, as you just mentioned. Sometimes in our optimization, we have to keep in mind if there is a robot that offers A, B, C, and there is another robot, we expect only job A from it, but it can do B, C as well. But we have another robot that does B. So if we bring these 2, in case the B drops out, the other one can offer. So we factor that in the first initial like team formation, that what are the redundancies that we can have later on we can use in the work. Yeah, of course, that's a very good, if it want to be scalable or sustainable, that's a very key challenge, because if you only have 1 robot that has, for example, it can go up the stairs, the others cannot climb up the stairs, and there is a search and rescue here, and the robot we have has to leave, or we lose that robot as part of a team member, then no one else can go the second stair. So we should have foreseen that in the optimization from the get-go. Absolutely, very important challenge in this design.
Yeah, thanks for the talk, and I like your design criteria, especially about the partial rate observability. So in terms of that, what kind of state of the human needs to be observed or estimated by robots? For example, cognitive state or emotions?
Yeah. A cognitive state, basically the cognitive ability. That's one of the, because I think the professor mentioned at the beginning, I also have a human factors team. They are looking at this cognitive ability of the human, basically through interaction. You know how much you can rely on this person, or how much attention of this person you have. Because if you have this technology, then you know how you can be more cooperative with human, or deliver new value for that human. For example, you have a companion robot that it not only interacts with you in a socially manner, but also it knows that it can detect your cognitive ability in a sense that you are walking on this street and it realizes you're looking the other way and there is a car coming from some other view that you're not looking. So it can raise that to you. It wasn't made to do that, but it can offer also this one. That's an important one. Emotion, as you mentioned, is another factor that needs to be factored. We have a study. I wish I had more time that I could, because these were only the computer science part of my team that I brought this. I wish I had more time and I could present some of the cognitive science aspects that we also do. That one, the emotion, we have a study. It's the paper is under review at HRI 2025 next year, which will be in Australia. That one, we are looking at aspects of emotion that factors this teaming. And surprisingly, it's not only the negative emotion that it affects your ability to achieve things. Sometimes having too much positive emotion does not necessarily, and it could be worse than negative emotion on the human machine cooperation. So that's very important to momentarily somehow regulate that emotion. And that regulation could be through distracting you from what you're thinking or any other way of regulating the emotion, depending on the type of emotion. But it's very interesting that we set up an experiment and we prove that having emotion impacts human AI teaming. Both positive and negative emotions are have significant effect on the human AI cooperation, so and teamwork. So that's also another interesting topic that we are looking at, emotion, and its impact on teaming. And of course, that's also a very these days very cutting edge area of research, especially for human factor. Yeah. Thank you for this.
Thanks a lot for the talk. I had a question about task allocation. So currently, the way I understand it, there are a set of robots for which there is a communication and the tasks are allocated amongst themselves. But sometimes it might happen so that once the task is started, you may find a robot which can do probably the task better than the current existing robot. So in that case, does the framework kind of swap your?
Yes. Yeah.
Oh,
Dynamic. Based on the situation and status of the task, and also availability and affordance of the agents that they can help with that. It's not something that you do it and then you continue and they do the job. If we want it to be a scalable solution, the same as humans, we should always give the robot this capability that they can say, no, I'm not following. So they can withdraw from the mission as we do. Of course, we take on many tasks, but halfway we realize that we have some other things that we need to withdraw and we do something else. So we say no. We have this saying no. We have the luxury of saying no. I think in a design, if we want it to be scalable, the robot should also have that. And it's very easy because, for example, the task takes more time than expected and the robot battery dies. That's one example. And that we cannot count on that robot anymore. Or that robot has a different primary task that is more important for it to achieve, and it has to take on that task. That's also a possibility. Yeah. Thank you for the question.
Thank you everyone for a question. Before I adjourn, I do want to share that earlier today, Dr. Moradi-Pari shared with me that HRI has every year 100 internship positions, like 2 positions for each of us in this room. So if you are interested, do talk to him, and I'll make sure to, of course, forward their opportunities to all the ICON students. We actually have a previous HRI intern sitting right here. But do talk to him and explore the opportunities. HRI is a great company. They work on a lot of those exciting stuff. But with that, let's thank the speaker one more time. Thank you everyone for coming.
Thank you.
Thank you for the stage. It's really a pleasure to meet you. My name is Ehsan. I'm actually an education student from Denmark. Oh, it's good to see you. And I was invited by a friend in here, and